So in this class, I want us to check the application of our Bernoulli's theorem or the Bernoulli's equation, which is on the tapered pipes. So in this case, this is actually, we are going to refer to a horizontal tapered pipe. What is it that you're supposed to consider in terms of the calculations? All right, so the Bernoulli's theorem in terms of the energy when given as energy per unit weight, we are going to see that the formula is going to be given as P1 over rho G. That is the pressure at the inlet, considering that is the density, the gravitational acceleration, the velocity at the inlet, the height that you're given, that is at the inlet, and also we talk about H2, which is the one that we end with, and this is P2 at the outlet. So what is it that we are actually having? All right, so I'm just gonna take this diagram to explain on that formula and what is considered. So this is a typical part that we have with the flow on a tapered pipe, which is a horizontal pipe. So we are going to see that in this case, the height being considered from the ground level up to the center point, or from the ground up to this, the height that we have at the inlet, which is our H1, is the same as our H2. So H1 is equal to H2. That is for a horizontal, So at the inlet, we must talk about the pressure, the area at the inlet, meaning to say we're going to talk about the bigger diameter. As we can see there, that's where we have a bigger circle compared to this one. So at the outlet, that is where we're going to talk about what? The smaller diameter to be considered. So it follows that the area at the inlet, which is our A1, is going to be given by pi d squared over 4. And the area at the outlet, which is our A2, is going to be given by pi d squared over 4, considering what? The smaller diameter there. All right. So this is what you're going to have in this indication. Then also in terms of the flow rate. All right. In terms of the flow rate, we are going to see that the flow rate that we have at the inlet is equal to the flow rate that we have at the outlet. That is in terms of the flow rate. And also it is important that we can also consider formulas that can connect V1 and V2, the velocities, because sometimes they might give you like what you see here. We have got the V2, we do not have V1. So we want to see formulas connecting what? V1 and V2. So we've got, let's just say, okay, so the flow rate is the same. This is about the flow rate here. This is about the flow rate. Remember, the flow rate is measured in cubic meters per second. All right, so that's another thing that you need to consider. Then also you need to consider the relationship. So you're going to need the relationship between V1 and V2, between V1 and V2. So there we are considering the velocities, and you must consider also how you are given your diameters, because sometimes you might be given something else, like in terms of the diameter. So consider like the direction that you are moving from. Is it facing the other way or the other way? So if it is like this, facing this way, this is our bigger diameter here, our smaller diameter at the exit. So you're going to see that. Remember, the flow rate is the same, and we know that the flow rate is the product of area and velocity. That is area in square meters, velocity in meters per second, which gives us what? Cubic meters per second. Square meters and meters, that's cubic what? Cubic meters. We are saying that this is the same. So using this relationship that Q1 is equal to Q2. All right, I want us to see something in the relationship. Since Q1 is equal to Q2, it follows that A times V on the inlet is equal to A times V at the outlet. So it now depends with what you want to calculate. All right. At the inlet, our area is given as pi d squared over 4, which is the bigger diameter there. That is what you have according to our presentation. So that will be pi d squared over 4 times V1 is equal to A2, which is the smaller diameter. So it's going to be pi d squared now times V2. So it is depending with what you want to calculate. Is it that you are given V1, you want to find V2, you're given V2, you want to find V1? So let's start with a condition where we are given, in this case, V2. Okay, you find V1. So given V2, we want to find V1. What you're going to do is to divide by pi d squared. So it's going to be pi d squared over 4 like this. Also, pi d squared over 4 like this. So this is going to give us V1. But I want us to see what is going to happen at the end. If we divide by pi d squared, you're going to see that these two cancel. The pi over 4 and the pi over 4 are the same. So that means we are left with the V2 times d squared actually over d squared. So that's the case there. We have got V1 in that case. So take note, considering the diameters and also the way that you're given, that will be the formula for V1. Let's say we were given V1 and we are supposed to find V2. All right, it can be like that. It's not supposed to be we are given always V2. So it can be a condition that we are given V1. So given V1 and we are supposed to find what? We are supposed to find V2. The formula is going to be taken. We start from this stage. Let's just start from here. Remember, we said from that stage, pi d squared over 4 times V1 is equal to pi d squared over 4 times V2. This time we need to find V2. So we're going to divide by pi d squared over 4 of the right-hand side, pi d squared over 4. So this will cancel. So that means we are left with V2 in this case. And just like the previous case, we're going to see that the pi over 4 and the pi over 4 will cancel. So that means we're going to cancel the pi over 4 and the pi over 4. We are left in this case with V1 times d squared. So it's going to be V1 times d squared over d squared. So take note there. Take note. The way that you're having your formulas there. Take note. So if you consider this, you'll see that, all right, let's have a conclusion on what is happening here. You'll see that if we are calculating V1, we are going to work with its diameter on top. So it's V1, its diameter on top. If we are calculating V2, its diameter on top. That's it. We have V1, but we are calculating V2. So we use its diameter on top. We are calculating V1, we use its diameter on top, because you might have a confusion on the diameter to say which one is going to be on top. So if you are calculating V1, you use the diameter for that V1 on top. If you are calculating V2, you use the diameter for what? For V2 on top. That's it. If you take it that way, you are not going to have a confusion. And knowing that always, because you want the velocity, so the velocity is going to be on top always. So that is the case. Maybe if you want to memorize it that way, because so far we do not have this formula from our formula sheet. So you need to know this. All right, so like I said, always when you are dealing with a horizontal tapered, we're going to take your H1 as H2. And also the issue of the flow rate is the same. So this is all, it also implies on the vertical tapered in terms of what? The flow rate. But in terms of the height, it does not apply. It only for a horizontal. So you need to know what you are working with. Sometimes they give us where there is an angle of where it is angled at a certain angle. It can be vertical. So you need to know each and every part. So make sure that you watch all the classes so that you're able to differentiate between these. All right, so that is what I think you need. And also the density there when dealing with water, because sometimes they might not give you the density. It follows that the density for water is 1,000 kilograms per cubic meter. So this is the density of water. We're talking about what? The density of water. So that is for water. That is what you're going to need. And sometimes, okay, someone might ask to say, why are we using these formulas? What if I'm given the flow rate and also the area? We can calculate V1 and V2 direct. Given flow rates and area, remember we said Q is equal to the product of area times the velocity, meaning to say I can also calculate this same V1 as V1 will be equal to it to be Q1, V1 like that. So it is just going to be Q1 over A1. All right, if I want V2, it means V2 is going to be, this will be 2, 2, 2 like that. So it will be Q2 over what? Over area 2, which is the area to the area that we have at the exit, in this case, from that pi d squared over 4. Remember, we've got a smaller diameter. At the inlet, we have got a bigger diameter. So that's it. So we can use this if we have these values. If this is given and the diameter is there, we can calculate it that way. But in case it is not given, then you are given V2. You are not given anything that can be related to V1, but they give you V2. You can use this formula. Or they gave us V1. There is nothing that you can use to calculate V2. We are just left with this formula. We are supposed to use this formula. All right. So I think this is it. This is what you need to attempt these typical questions on horizontal tapered pipes. So we're going to check these questions, guys, so that we see how we are supposed to attempt these typical questions. So there we were given in this case. All right, let's consider our diagram, in this case, our information. All right, so they are saying in this case, water with a density of 1,000 kilograms per. So there we are given the density, which is fine. Okay, it's okay. So the density there is given. So we're given that water, it has got a density of, so the density of water, which is 1,000 kilograms per cubic meter, flows through a tapered pipe, which is a large diameter of, so this is the large diameter, this side of 0.65 meters, width, and the smaller one of 0.45, this side we've got 0.45 meters. The pressure gauge at the smaller diameter, which is at this side, at the outlet, the pressure is 16 kilopascal. That is the one that we are given there. And the flow velocity is at this smaller diameter, meaning at the exit, the velocity, which is V2, is 20 meters per second. Find the pressure reading at the larger diameter of the pipe, which means at the inlet, what is the pressure reading, which is P1. So we need P1. So because we are given that this is a horizontal tapered, they are not going to even give us the height. If they want, they can give us. But they know that H1 and H2 are the same. Remember, we said that H1 and H2 is the same. So it means there is nothing that you're going to consider on that part, because H1 minus H2 is going to give us a 0. If they are the same, if you take one to the other side, remember H here. Okay, this is what I'm trying to say here. This is our formula for the energy. So if I take this H1 to the other side, what happens? It will be minus H1, so it subtracts. So it simply means we are just left without H1 and H2 because they are the same. So you're just left with this part of the formula only. This is the part of the formula that you're going to need. All right, remember we want to calculate the pressure at the inlet where we have a smaller diameter there. So I'm just going to take our formula. So remember from our Bernoulli's theorem, it is stating that, all right, guys, I hope you remember these formulas. Because of space, I'm just going to need to erase this. All right. So the formula states that from our Bernoulli, remember that P1 over rho G plus V1 squared over, that is 2 times G, plus H1 is equal to P2 over rho G, which is just a repetition of what we have here, plus V, so it's going to be V2 squared over what? Over 2G, plus it was H1. So here it's going to be H2. So that is what we have. But remember, these two are equivalent, H1 and H2. So it simply means we do not have this. We want to calculate this one. All right, P1 we have, the density we have, G we have, density we have, G we have, V1 we do not have, G we have, V2 we have. So meaning to say we have to calculate V1. We are given V2. We are not given the flow rate. So we can't use that formula that I said that we can use V1 is equal to Q1 over what? Over area 1. We can't use this because we do not have the flow rate. Yes, we've got the diameter, you can calculate the area, but the flow rate we do not have. So we are back now to that formula that we manipulated between V1 and V2, if you still remember these two formulas that we have here from our manipulation. I said we can calculate V1 and also we can calculate V2 depending with what you're given on the information and what you're supposed to calculate. Then we want to calculate V1, so we can use this, where V1 goes with the diameter corresponding to V1 on top. So that is the formula that was going to be very, very applicable to calculate our V1. Okay, so that is it, guys. We manipulated these. We saw where they came from. So it means V1 can be calculated from V2 times the diameter at V1, which is D2, which is D squared over the other diameter at the, the diameter. Guys, here I just got a confusion to you guys. This is V1 opposed to the diameter. V2 opposed to the diameter, guys. Guys, I'm just very sorry for that because this is D on the other side. All right. So if you're calculating V1, the diameter on the other side, guys, let's just hope you remember this. Let's just hope you remember this. So this is V2, the one that you're given. So V2 is at the exit, so it's 20 meters per second. So we are going to multiply to D squared in this case, all right? Or you can even calculate the flow rate. You can even do it that way to calculate the flow rate, all right? But you can use this one. So it is gonna be D squared, which is this one at the exit, 0.45 squared. All right, then we also have the diameter that we have in this case at the inlet. So there, like I said, guys, please just forgive me on this part. This is supposed at the inlet, which is 6.5 squared. So my explanation was actually something else. It was actually something else. It was actually something else on this part. All right, so this was going to give us V1 was going to be something like 9,586 in meters per second. That's where we've got a V1. So yes, we can calculate those Q1 if you want. You can do that. I'm not saying it's wrong. You can do that. But if you've got these formulas, guys, they are direct and straightforward to understand. So let's just talk about this again, maybe. Said V1, in order for you to have V1, is going to be V2 times D squared. So this D is the diameter on the other side. V1, the inlet, this is the diameter at the exit. This is the diameter at the inlet, the bigger diameter. So guys, consider that on the diagram there. D at the exit, D on the inlet. All right, if you consider V2 is going to be V1 times D squared, which is D squared, this one at the inlet. This is V2 at the exit, D2 at this D squared at the what? At the inlet. So just consider that this is inlet, but the diameter that you take is at the exit. This is exit, but the diameter that you take there is at the inlet. So can we just correct this part? Please, guys, can we just correct this part? All right. So that's it. Like I said, we could have calculated the same from the flow rate. Let's say we have the flow rate. All right, how so? Remember, I also stated that the flow rate concept there is the same. We're gonna have the same value of the flow rate in that case. All right, guys, let's just hope this board is gonna allow us to finish here. because the way that it is reacting, I just do not know. All right, I just do not know what's happening now. All right, anyways, so I was saying the flow rate that we have is the same. So meaning to say Q at the inlet is the same as Q that we have at the outlet. Let's see if we can win to calculate velocity from there. Q at the inlet is equal to Q at the outlet. This is our flow rate, which is simply, we are talking about the area at the inlet times the velocity at the inlet, the area at the outlet times the velocity at the outlet. So considering that area 1 can be calculated, area 2 can be calculated, remember, we have got the diameter here. So it means this one was going to also work. The area 1 at the inlet, we are going to use the bigger diameter, so it will be pi d squared over 4. At the exit, our area 2, we're going to use the smaller diameter, which is going to be pi d squared over 4. All right. So with this, we can have our values in this case. All right. So that means, okay, let's just calculate our areas here. Guys, very sorry for this. So that means our area 1 is going to be pi times the diameter squared, 0.65 squared over 4. So that's we're going to have the diameter from, or let me just use it, let me just use it like this so that we have exact values, so that we obtain exact values in that case. All right, let's just leave it like that. Let's just leave it like that. So in this case, the question is, what about the flow rate? Because it's either the flow rate is the same. So the flow rate, we're going to obtain it from area 2 times V2. Because there we have got everything that is complete here. We have got area. We also have V2 in this case. So here we are going to calculate the flow rate at the exit Q2, which is area 2 times V2. Remember, area 2 is pi d squared over 4. That is pi d, the diameter at the exit, 0.4. 5 squared over 4 times what? V2, which is 20. So this is going to give us Q2, and that was going to be 3,181 cubic meters per second. But remember, I said Q1 is also equal to Q2, so it is also equal to 3,181 cubic meters per second. So if we have Q1, that means we can be able to calculate V1 because we've got area 1 here. So that means our V1 from this information was going to be given as, so that means our V1 from Q1 over area 1. So that's our Q1, which is the one that we calculated. Remember our Q1, we got 3,181. So you're going to divide by area 1, which is pi d, which is this one. So that's pi times 0.65 squared, everything over what? 4. All right, so this was going to give us V1, which is the velocity at the inlet. And that was going to give us 9,586 meters per second, which is the same as the one that we got here. But as you can see, this one is a little bit tiresome. We've got a lot of stages to consider. But if you know that, it's an advantage. If you can know this, then it's an advantage to you. In your simplification, it's very, very good to know that. But this is a direct question, a direct formula, as we can see. All right, so let us see that we have calculated V1 because that was the missing part here. Now we have got V1, we can calculate P2. So we're going to insert our values there, P1 over everything. All right, so our P1 is the pressure there. Remember, we need to calculate P1 given, find the pressure reading at the larger diameter. P1 is the one that we are supposed to calculate, this one, given P2. Guys, how I was taking this information. All right, so let's just hope, guys, you find it easier to understand even after all these confusions. So this is the P1 that we're going to have, P1 over the density. What was our density in this case? The density was 1,000 kilograms per cubic meter. Like I said, you might not be given. You're supposed to know the density of water. Then times the gravitational acceleration, which is 9,81. So that's 9,81 plus V1, which is the one that we calculated our velocity. We got 9,586. So it's going to be V1 squared. Everything over 2 times the gravitational acceleration again. Then, like I said, H1 and H2 are the same, so they will cancel each other. So it's going to be equal to P2. We have got the pressure at the exit, which is 16 kilopascal. So that's 16,000, or 16 times 10 to the exponent of 3 kilopascal. The density again, 1,000. That's 1,000 times 9,81 plus V2, which is the original value that you're given there, which is 20. So that's 20 squared. So you're going to have 20 squared over 2G. So the simplification there, guys, it depends with the way that you want. So as for me, personally, I prefer it this way, to just simplify this part. P1, then multiply this to 1,000 times 9,81. Just multiply, you get the exact value, so that we do not have, like, at the end, those much values which are being affected. So this will give you 9,810 if you multiply 1,000 times 9,81. Then simplify this from your calculator. All right, so guys, why am I repeating 2G there? This is 2 times 9,81. So simplify this on your calculator. You are going to obtain something like 4,684, equal to, combine this whole part, everything there, combine it. So that will give you 22,018. So that's it. We can calculate our P1 from there. All right, so we can transpose this to the other side. It becomes a negative. So we're going to remain with the P1 in that case, which is the one that you want to calculate. So it's going to be P1 over 9,810 is equal to, if I transpose this, that means I'm going to subtract. It was a positive. So on this side, it is going to carry a negative 4,684, like this. So that means we are going to have at the end 17,334. So to find P1, what are we going to do? We're simply going to cross multiply both. This is the same as over 1. So we're back to equations there. This will multiply this side, multiply this side. 1 times P1 is P1. And these two will multiply each other. 9,810 times this value. It is going to give you 17,004.6,54, which is pascals. So if we divide by 1,000, converting to kilopascal, that means our P1, if we divide by 1,000, is going to be 17,004, which is just approximately 17 kilopascal. That's the idea there. So that's how we can have this. The pressure there. What is the pressure that is corresponding where we have a bigger diameter in that case? All right. So that was the condition of our question, where we have a larger diameter of the pipe. We're supposed to find the pressure, which is P1. So we can use our Bernoulli's theorem. But are you considering the information properly in using the Bernoulli's theorem? That is what you're supposed to consider. Make sure your information is properly presented. What need to be calculated must be calculated, and no, the height is the same. All right, let's see another part of our question, which is similar to this. There we are given P1, that is Fig 7.8 in that case, shows water with a density of 1,000 kilograms per cubic meter. So we have given the density of the water, which is 1,000 kilograms per cubic meter, flowing through a tapered pipe. The larger diameter of the pipe is 130 millimeters. So if we divide by 1,000, it means the bigger diameter will be 0.13 meters. The smaller one is at 105. Divide by 1,000, it will be 0.105. So it's going to be 0.105 in meters. For the smaller diameter, the pressure reading is, which is 125 kilonewton per square meter, meaning to say we are given 125 kilopascal. And that of the larger one is given as 150 kilonewton per square meter, meaning we are given P1 as 150 kilopascal. Calculate the flow rate in liters per second, which is the flow rate, it's Q. Remember, Q is supposed to be measured in cubic meters per second, but there they need this flow rate in liters per second. All right, we'll talk about that later on, the issue of conversion. But as you can see, we need the flow rate. We need the flow rate. So where are we going to have the flow rate? That is the question. Where are we going to have the flow rate? So in order for us to have the flow rate, it's either we must have velocities. In order for us to have the flow rate, we must have velocity. That is what we know. That is what we know. The flow rate, which is Q, is area times velocity. There we have got the diameter. We can calculate area, but no velocity. There we have got the diameter, no velocity. So we can't calculate the flow rate. No matter we know that this is the same, Q1 is equal to Q2, H1 is still on horizontal, H1 is equal to H2. It is limiting us. So that means we have to calculate V, either V1 or V2. We need to calculate either V1 or V2, because once we have V1, we can calculate the flow rate. We have V2, we can also calculate the flow rate. All right. But now we are stuck. We do not have anything to use. All right, let's go back to our Bernoulli's theorem. Maybe it can assist us to calculate something. Our Bernoulli's theorem, again, this is a density there plus V1 squared. So you're going to have V1 squared over 2G. All right, plus H1 is equal to, that will be P2 over rho G. Density times gravitational acceleration plus V2 squared, which is the velocity over 2G plus H2. This is it. So the question is, all right, we understand that these two are the same, H1 and H2. They are the same. So this will cancel. So it's either, all right, I'm given also here, let's consider P1 and P2. They are there. We are given, we have got P1, everything is there. We do not have V1. We have got P2, everything is there. We do not have V2. So it means it's either we have to calculate V1 or we have to calculate V2. That's it. It's either we have to calculate V1 or we have to calculate V2. All right. If we were to calculate V1, I want us to see this, or V2. Remember, I wrote those relationships between V1 and V2. Maybe we can win from there. We said V1 is taken from V2 times the diameter at the exit. If you're calculating V1, you use the diameter at the exit, which is D2, which is D squared over D squared. If we want V2, we are going to use V1 times the diameter at the inlet, which is D squared over D squared. This is what I said. So it means I can write my answers in terms of V1 or in terms of V2. So if I want to have my answers in terms of V1, it means V1, I mean, in terms of V2, it means V1 is going to be equal to V2 times D squared, the diameter at the exit, 0,105 squared. Everything over D squared, inlet, 0,13 squared. So this is going to give us V1. In terms of V2, so that's 0,652 V2. So V1 can be written in terms of V2. So if V1 can be written in terms of V2, it means we have it, so we can calculate V2. We can calculate V2 if it is like that. Because there we're just going to substitute. Okay, let's substitute and say P1 is what? 150 kilopascal, which is, we've got V1 there. 150 kilopascal, which is 150,000. Remember, the density of water is 1,000 times the gravitational acceleration of 9.81 plus V1 in terms of V2. We calculated this in terms of V2. We got 0.652. So it's going to be V2 squared. Everything over what 2 times the gravitational acceleration of 9.81 is equal to, because these two are the same, so they cancel. P2, we have got this pressure. At the exit, our P2 there, it was 125 kilopascal. So meaning to say, this is equal to 125,000 times 10 to the exponent of 3. The density of water, 1,000, gravitational acceleration of 9.81. Plus V2. Since we can see that V1 is written in terms of V2, so it means I can also write this in terms of just V2 as it is. That's it. So by solving this equation, by solving for V2, we are able to calculate the flow rate, because the flow rate is area times what? Velocity. So we must have the velocity there. We are supposed to have a velocity from there. Okay, so let us just try and see the way I simplified here, guys. I just simplified this together and got a value there, which is 15,291. I simplified this I simplified this is this way. It's 0,065 squared over this. So it's 0,65652 squared, like this, over 2 times 9.81. So this is going to give us a decimal there, which is 0,0217, something like that. And V2 will be raised to the exponent of 2. So it's going to be V2 squared. All right, you do the same thing on the right-hand side. You simplify. So there, we're going to simplify this together. We get a single value, which is 12,742 plus. So there, I want you to divide like this. 1 divided to this. 1 divided to 2 times 9.81. You're going to obtain 0,051 with V2 squared. So that's it. So you can simplify this way. If you understand it, then you have to collect the terms with V2 to one side of the equation, because you have to solve for V2 in that case. All right, so I'm going to take this way, this side. I'm going to take this V2 to the other side. So if I subtract 12, so it's going to be 15,291 minus 12,742 is equal to this 0,051 V2 squared minus 0,0217 V2 squared. So combine this, we're going to have a single fraction there. And this will be 2,549 is equal to, you subtract these two, since they are in terms of V2 squared, so we're going to subtract this minus this. So if we subtract there 0,051 minus this, is going to be 0,0293. That will be V2 squared. So the question is, how are we going to have V2 from here? Definitely, they will need the square root. As you can see, there's a square. So from our mathematics there, we introduce the square root to remove the square. So that means we've got V2 as, sorry for that. So in actual sense, the square root of this, we're supposed to have this first. Let's do this before. For this, let's divide first. Before we talk of this square root, divide by this 0,0293. Divide by 0,0293. So this will cancel, and you've got V2 squared, which is this. So this is 2,549, everything over what? 0,0293. So with this, now we can introduce the square root. We are left with a single term on one side of the equation. So that will be the square root this side, the square root this side. V2 is going to give us 9,327 meters per second. So this is due to the rounding off. This we cannot have maybe exactly the same value, but you're supposed to have an approximate of this. So with this information, guys, it is, all right, remember we wanted to calculate the flow rate and we are stuck because we do not have the velocity. So since we, at the end, we saw that the velocity that we calculated is the velocity at the exit. It's V2. So it means the Q is going to be A2 times V2. That's the flow rate. A, which is the area that we have at the second part, which is pi d squared from the smaller diameter. All right. So that means in this case, we can be able to calculate this. All right. There we have got the velocity only, but we need the flow rate. So Q, since Q is equal to the area times the flow rate, the area times the velocity. So therefore, we're going to have the Q at the at this second part, which is Q2, is going to be area 2 times V2. Since we calculated this, we can calculate our flow rate. So that means our Q2 was going to be equal to A2, which is the area. All right, area 2. We are considering the area that we have at the, okay, so we've got a lot of information here. This area at the exit, that's the second part. So you have the diameter 0.0105. All right, so that's our area. There is gonna be pi d squared, small letter d. All right, so let's see there. The smaller diameter we are given, as we stated there, it was 1.05. So sorry, 0.105 squared over 4. All right, then you multiply to V2. Already V2 is there. So that means our V2, 9.327. So this is going to give us the flow rate, which is Q2, which is equal to that's 0.0808 cubic meters per second. All right. But there, the recommendations of this answer is, it is supposed to be in liters per second. Not this, but liters per second. So how are we going to convert now our flow rate? Because the flow rate is the same. Q1 is equal to Q2. But from there, how are we going to write this flow rate in liters per second? So you're supposed to also understand that if we are dealing with the volume, each cubic meter is equal to 1,000 liters. Each cubic meter. So to convert to liters, we simply have to multiply by 1,000 on our answer. So therefore, our flow rate Q was going to be 80.8 liters per second. That's it. You have your answer now direct to what? Liters per second. So due to rounding off of values, our answer, they tend not to be the exactly, but they are exactly what is needed. No matter how it looks, let's make sure that you round off properly at the end. All right, so this is good. This is it. This is how our questions might be like on a horizontal tapered pipe.